All right, so we have vector -295 and 1, -1, 0. We want to find the scalar product and the or scalar multiples and the difference and all that good stuff. So the parts B and C, they don't, they're not really proofs, but they kind of take the form, or at least the quality of something that could end up being a proof, because this could very easily become k times the magnitude of W is equal to, and we want to see if that's equal to the magnitude of k times W. So, you know, because you always want to kind of keep that in mind. You know, anything property related could take the form of a proof on a test. All right, so for part A, you could probably do it in your calculator. I mean, you could definitely do it in your calculator. It's just a question of whether it's worth it. I don't think it is in this case. So I'm going to rewrite V again in the bracket notation. And W also. All right, so we're looking at 3 times -295 minus 2 times 1, -1, 0. So -6, 18, 15 plus -2, 2, 0.
Shouldn't that be 27 instead of 18?
Oh, yeah. Thank you. So -8, 29, and 50. So it's going to box it, but it's not going to look so good. So let me do, I'll just leave it at that. All right, so just the sum of the two sets of components. Go red. Ooh, always go for the wrong one. All right, so magnitude of W. Just crunch that out right quick. One squared plus -1 squared plus 0 squared if you want, but you could obviously leave off the 0 squared. So √2. So therefore 5 times the magnitude of W would be equal to 5√2. All right. And you know, just for fun, in general terms, right? Because if I'm not going to assume that the 5 is a constant, then I'm not going to assume that W is particular. We'll assume that it's in general terms. I'm not sure why I had to walk over there to point that out. Now, for the magnitude of 5W, you can find the product of 5 and each of the components first and then square them. All right. I'm going to kind of itemize it a little bit and write it as 5 times 1 squared, which obviously is the same thing, but it's going to serve a greater purpose in a second. 5 times -1 squared plus 5 times 0 squared. Because the 5 times 1, 5 times -1, and 5 times 0 is what you would have done in order to get your 5W vector. So if I wanted to up here, I could have just written 5 w equals 5, negative 1, 5, negative 1, 5, negative 5, 0. All right, so it amounts to the same thing. It's possibly an intermediate step that you're not interested in doing, but if you write it this way, then we're looking at something that factors, because you have a common 5 squared for each component. So you can factor that out and be left with 1 squared plus negative 1 squared plus 0 squared. Which would be equal to 5 times the square root of 2. All right, because the 5 squared, the root of that is a factor, pull that out. Square root of 5 squared is 5. And this whole component here, well, we already did that up here, that gave us a root 2. I mean, you could also figure it out in here. All right, so that sets us up for a possibility of having something like the magnitude of kW bless you. So that would be k times W1 squared plus k times W2 squared plus k times W3 squared. Again, GCF of k squared factor out, well, we already have a factored out form of k squared, but the root of that, because it's in factor form, would be k. And so what's left in the radical here is what was in the radical for part B, if we were to do it in general terms. Right? So, we weren't asked, but we basically, more than basically, we proved the relationship. Right? Not coincidentally, maybe we just got lucky here. We proved it in all cases. The one thing to be careful about on a test, and people fall into this trap all the time, just be careful about the space. This is in R3. This is everything we're doing in this little mini packet is R3. So, little side references here and there, but the main scope of it is related to R3. So, on a test, it could say R2, it could say R4. It's all essentially the same thing, conceptually. But obviously, you don't want to throw away the. I think it would be half a point if I said to do it in R2, but you did it in R3. Yeah, three variables, 3 dimensions. Real space for x, for y, for z, x1, x2, x3. Yeah, so I think it would be a half-point deduction. I'm just thinking in advance. Half a point deduction if you did it in R3, but I asked for R2. Just for, you didn't follow instructions. You did it out the right way, you just didn't follow the correct instructions, so half-point ding there. If you did R2, but I asked for R3, it'd probably be a full point deduction, only because you kind of let yourself off the hook with some writing that other people would have to do. So just to kind of make it a little bit more equitable, I'd probably do a 1-point ding there. So. Unit vector in the direction of v. So we need the magnitude of v. So root -2 squared, 9 squared, 5 squared. 85, 110. I think I don't know. Unless I'm right, then in which case I do know. All right, well, you had your chance. All right. Because if it was wrong at this point, I'm not changing it because I just wrote it like 4 times. So. And so again, the idea here is that the magnitude of the unit vector should be equal to 1. Right, so if I were to ask you to verify that this is actually a unit vector, which of the following 3 vectors is a unit vector? Not that I would ever give a multiple choice question, but that's an example of a type of question. But I could say, determine whether the following is a unit vector. I think it'd be overly simple for a test, but all you'd have to do is square the components, see that it adds to 1. In terms of questions on the, sorry?
Suppose adding from -2 over radical 100.
Square this, square that, and that, add them all up, and then root them, and you should get 1 as a result. So that basically you're taking these components and putting it into this formula. And it allows us to redefine a system in terms of new bases. So that's something that we want to kind of keep in mind as we move forward, right? So have it in your mind, even though it's not directly going to be referenced very frequently, we will come back to it, and it'll be the foundation of something known as a change of basis. Although we do have shortcuts, so it's like a theoretical component, and then it's like, well, actually, if you just do a reduced row echelon form and then multiply this by that and call it, like